Everybody. Today's speaker is Dr. Hossam Gaber from OntarioTech University. He will be talking on resilient nuclear renewable hybrid energy systems and the integration of nuclear renewable to support energy infrastructures. He'll present different coupling mechanisms to support different user requirements and installations, and outline design and operating strategies for the use of these nuclear hybrid systems in different applications in city, urban and remote communities. Dr. Gaber is a full professor in the OntarioTech University in the Faculty of Energy Systems and Nuclear Science, and cross-appointed with several other faculties and labs. He's a recipient of the Senior Research Excellence Award for 2016 and recognized as one of the top scientists worldwide in the area of energy. The integration of nuclear and renewable hybrid systems is an area of particular interest to us in Wisconsin. I know many people on this talk have some interest in this area, so it's great to have you here today, Dr. Gaber, and the floor is yours.
Thank you very much, and I'm very pleased and delighted to be with you. And thanks for the invitation. It's a great opportunity to share research and also exchange ideas and innovation and applications to industry as well, in particular with the expansion of nuclear industry and nuclear power plants to integrated nuclear renewables for different applications. So my talk, as you see, resilient nuclear renewable hybrid energy systems. And at first, I would like maybe to give a quick introduction about maybe our university. We are a new university established in 2002. So we have like started the first that I would say when you start university, you would like to establish the best out of everything. So that's where they started actually. So they started really very strong infrastructure, communication, IT, networking. And in particular, we are located in Toronto. So this is Toronto, which is southeast of Ontario. Our university is east of Toronto. I live in Toronto, but it's commute around 50 kilometers. These are the buildings we have. Actually, this field here is a geothermal field, which is, again, one of the largest in the region. It has 116 or 112 feet under the ground that can provide the thermal heating and cooling during the two seasons, and also support the energy for the different buildings. We have new buildings happening. So we have, this is one of our new building software it's called Software and Entrepreneurship Research and Innovation. So it is a new facility that's recently established. This is our library in summer and the library in winter. I guess you understand what's winter in North America. So at first, I would like to say that this work have been done by mainly with my two master's students, Muhammad Absami and Rafiul Absami and Ibrahim Adham, but also with the help with other scientists, researchers, and postdocs in my lab. My talk will be primarily talking about integration of nuclear renewable and some strategies and design, and also potential application, techno-economy analysis, and some case studies with deployment considerations and operation and control strategies. At first, and before we talk about nuclear renewable, I started this work actually in 2003 around in Japan, where I was professor there in Okayama University, and in 2004 actually. At that time, I started looking into what is a problem? Like, why do we need hybrid energy, and why we don't just use one source like nuclear power plant and that's it? So at that time, I started looking into regions and available resources. So as you see here, we have hydropower plant, wind, solar, thermal, and nuclear power plant, and they are scattered in different regions. So we sort of divide the region into different sub-regions, and we say, okay, if we are able to satisfy the energy requirements in each sub-region, that means naturally and eventually we are able to satisfy the energy demand in the overall picture. So what we have done at that time, is I modeled this area actually, and I mesh it in a mesh with a GIS, geographical information system, and I capture information from each cell, like number of vehicles, number of persons, number of plants, buildings, cars, and then emission and the energy, and we try to balance those to be able to calculate what really do we need and what is the best way to move forward. If our demand is increasing and the resources are sort of limited and not meeting the demand, then definitely we need to find solutions. In Japan at the time, the biomass is eventually one of the largest, and the hydropower. We have a lot of rivers, and the hydropower is quite large, but also the biomass, where the buildings are built from, like wood. We got the chips from the building after demolishing, maybe due to earthquakes and so on. And those buildings, those wood or biomass, we chip them and then we put them in gasifiers. We get energy, thermal energy. So at that time, we have to make a decision which option is the best. And in order to do that, there are a number of factors, as we see: resources availability, and also greenhouse gas emission, and some other factors that it is eventually the cost is one of them, and the life cycle cost, levelized cost, which is also important. So at that time, we studied this picture, and I tried to come up with a solution where I try to make it automated. So I generate numbers, thousands, and actually I reached like maybe more than 400, 500,000 possible scenario for different regions. And each scenario means strategy, different energy technology. And based on that, we try to analyze them and come up with a performance. So that's where we reach the first stage. After that, I found that it is important that I also think about modeling blocks for energy, for any energy system. So if you see, this is a sort of a building block. Like this, the building block has inputs and has output. So for example, if you have thermal input and thermal output, this looks like a thermal storage unit, and so on. Now, the energy modeling part, which is an abstract way, it's not necessarily just thermal or electric or fuel gas, but it's also work, like the thermodynamic law, so something that you need to do something, move something, like maybe a motor, engine, generator, turbine, and so on. So you need some usage out of that, which is the work at the end. In addition, we have some other things like light and some other maybe mixture between them. So at that time, when I was doing that analysis to come up with what is the best actually to move forward, I needed to build these model libraries. And the model libraries will allow us to first understand in abstract manner what are the possible conversions, even some of the things that might not be available. Like for instance, at that time in 2004 and 2003, there was no clear cut about like fuel cell in terms of like advanced, of course, it's all but advanced technologies, fuel cell, gas power gas, or power gas power conversions, and so on. So that's where I started looking into things like applications. Like now, as of now, we don't have hydrogen barbecue, for instance, or hydrogen boiler, but we do have hydrogen fuel cell. So accordingly, there are things which we can think about. Eventually, for instance, like a vehicle, we can have IC, internal combustion vehicle, but also we can have hydrogen fuel cell vehicle. But actually, we can have naturally like compressed natural gas vehicle or hydrogen vehicle, not fuel cell, but hydrogen vehicle. So that is a technology. And that's where I started building these generic and generalized building blocks and use them for the analysis of this picture to create some scenarios. And this work is actually published also at that time. So we have a number of scenarios, and these scenarios could be going this way up to the cloud, and then this goes to the end user, which is house, building, factory, road, equipment, vehicle, and so on. And each of these scenarios, I associated this with some constraints, like this constraint number. So each constraint represents some either policy or regulation or actual physical limitations or some requirements. And based on those, I embedded that into the model so that I actually able to generate and evaluate the scenarios to achieve the best possible combinations. At that time, actually, I thought about something very interesting, and I believe that I was one of the first people to think about smart energy grids at that time in 2003 and 4. And that's where I found that it is possible that, for example, if we have a building like in your campus, you have a natural gas pipeline coming in, and you have a thermal, maybe pipelines and thermal storage and so on. And you have the power, electricity, and you might have network, and you have some other cables coming to the building. At that time, I thought, what about we think about this cloud, like internet energy cloud or energy Internet of Energy, or electric cloud, which means I convert everything to electricity and I just move electricity across places. So in this case, instead of extending natural gas pipelines, I just extend power cables. And if I want to get any natural gas or hydrogen, I can actually generate hydrogen by electrolyzer and fuel cell, for instance. So that's where I started looking into different extremes and evaluate them with different scenarios. Now, those constraints and scenarios I worked at that time was a couple of companies in Japan. We have a sort of something like central energy utility company, like Central, where it can cover transmission and distribution in the whole infrastructure, including gas and electricity. So that's where we talked to them. What about we can create this picture? And when we come to the end user, we develop what we call those microgrids in the end user side with energy storage. So that is where we have been looking like the picture. I made a couple of extremes so that I can have like very extreme where all is electricity, and the other extreme is everything is hybrid. And in between, we can make variations. Here, I use thermal conversion and thermal storage. And after that, when I went to the big picture, I have to go down up to the end user, like a building, a campus, a factory, a farm. And based on that, I started looking into the lowest possible, smallest level, which is a micro energy grid. So the micro energy grid, which is combinations between, like as you see here, transportation network, water network, thermal network, electric network, and the gas network. And the gas could be natural gas, compressed natural gas, or could be hydrogen as well. And in between, we have the connection and transfer between them. So we have here two-way communication, which is the transfer of from the infrastructure, like a water network. We can get water into the building, or we can get water from the building if it is treated water or processed water or stored water, and so on. Same for electricity, gas, and thermal. By this way, it's in a generic form, we are able to build what we call this superstructure in this way, which is something like really dynamic, adaptive superstructure, where at any point of time, if we have power outage here, like if we have power outage here, I can transfer through this building, for example. And this could be even two ways in the same way. Or we can exchange between these two buildings in the outage and need and demand based on pricing and based on performance and so on. So I included at that time some prediction of gas price, electricity price, and the weather forecasting for the thermal. And based on that, we were able to say what is the best possible scenarios between microgrid 1, micro energy grid 1, micro energy grid 2, and the transmission. One point I want to highlight, the definition of micro energy grid, it was really meant, as we know, for people who are thinking about microgrid, they always think about AC-DC line. So if we have an AC line and DC line, and this AC-DC, usually it's a microgrid. But in my case here, I was talking really about micro energy grid, where I am talking about hydrogen flow, thermal flow, natural gas flow, water flow, and transportation. So in this picture, I built this as sort of a comprehensive model, like a model house or model library, where I can have here a compressed natural gas vehicle. So CNGV, compressed natural gas vehicle, or could be EV, like electric vehicle here. And here we have the water supply, we have the natural gas, and we have the hydrogen supply, and so on. So by this way, we are able to get like the most possible complicated or comprehensive different approaches to be established as a microgrid. Here, I also included things like waste to energy. Like we get the waste with gasification and pyrolysis, we can generate high value gas or like actually clean diesel or clean oil, and also for industry and transportation. But also we can generate electricity out of the waste. And based on that, we are able to link them with the comprehensive picture. Now, as we know that this is a comprehensive model that can be implemented in different places. And if we implement this in northern area, might be different than if we implement this in southern area where we have like thermal. And that is the variations and the parameters and configuration can be adjusted. Same for availability. If we do have natural gas, we include it based on the price prediction and availability. If we have thermal, if we have electricity cost is very low, and so on. So it is adaptive. And I mentioned a couple of things here about food and health and water supply because of course, COVID, where we found some places where there is no oxygen, there is no power supply, and that impacted many aspects of our quality of life. Accordingly, this micro energy grid is not just necessary for energy, but actually it is related to food and health and water. We had a blackout at the time, one time a few years back in our nuclear power plant, we had a blackout, and also in the electricity as a grid in transmission distribution line within our region, we had blackout. So I have to actually, when I go to gas station, we don't have gas because the pump is not working with electricity. So I cannot put gas in my car and so on. And in our house, the heating cannot work because of the electricity. So it was a sort of a disaster, but that's where the hybrid system can allow us to have resilient energy systems. So the combinations between them will lead to the best possible microgrid or energy, I would say, scenario. Now, what do we mean by best? So I started quantifying and analyzing and modeling. What do we mean by best energy system, hybrid energy system? And I'm preparing that before I go to the nuclear renewable, because this is very important. When we talk about nuclear renewable, we will talk about best scenario. What do we mean by best? So we actually modeled sociocultural parameters, economical parameters, environmental, reliability, technical, which is a comprehensive view to think about how, if you have an energy system and you'd like to say it is good or bad, how good, how bad, you'd like to give it a percentage as overall percentage, you would like to evaluate based on all of those, not just cost or reliability or even quality. So that's where I created those parameters to be able to evaluate them. And the parameters, I linked them based, if I have a microgrid based on components like PV, SMR, and so on, wind and generator and so on. Each of these will have a set of variables, like maybe the PV, it's a process variable. It's like maybe the height, the weights, the dimension, the capacity, the power rate, and so on. And based on that, we group them into KPIs. And overall, we put weight for those KPIs, and the summation of all KPI I over from I to 1 up to N, for example, we are able to get the summation to get the actual value of overall KPIs. In addition, we also quantify the risk. So the risk, although it is so always when you go to any industry or energy systems, they are very clear about the risk as the risk is a likelihood of and the magnitude of consequence, which is L times C. However, what we are saying is the probability of failure here have to be related also to that value. Like if I tell you that I'm going to install a hybrid micro energy system with SMR and wind and solar, it's not enough to say how much it will cost and how long, but I have to say that it will be reliable, that it will not have any interruption for a certain period, which is the probability of failure on demand, which is related to probabilistic approaches. And that is where we develop this Bayesian belief network to be able to evaluate what is the cost of losing electricity for 1 hour. So that's where we were able to integrate that, and based on the cost of losing electricity in 1 hour, that will be reflected to cogeneration and the resiliency and the value of the nuclear renewable. And that's where it took us to IPL, which is independent protection layers, and the PFD is a probability of failure on demand. This, of course, this is detailed concept, but it is, if you feel that you need to have a resilient energy systems, that means probability of failure should be very low, and that means you need to add more additional protection layers. As a resiliency, the protection, like in terms of safety, protection layer is alarm, shutdown system, and maybe redundancy. But in terms of resiliency, the protection layer here or resiliency layer will be cogeneration and storage. So if you have more storage, even if you have power outage, you can use the storage for a certain time. So I try to link the resiliency with the risk, and they created those concepts of IPL and the independent resiliency layers, and I captured that, and that was also published and analyzed. Now, based on that, we are able now to talk about how to introduce the nuclear renewable really as a motivation here. So we would like to introduce nuclear for a number of reasons. It is sustained, it is sustainable, it is clean, and it is reliable. And it has, especially SMR, when we talk about SMR, which or MMR, macro modular reactor, or SMR, small modular reactor, that they are expected to be sustained and stable. There's no additional burden of operation, change fuel, and so on. And the only thing, and also there's no generated local waste in the region. However, there are some waste could be generated for maintenance and inspection and so on. However, it is minimum. Also, itself, because it is a stable energy source, it can cover, I would say, the base load. But for the availability of local resources and RES, which is like renewable energy sources, we are able to integrate and get the best out of both. The energy is that it can be a sort of availability most of the time, and also resiliency. And for any reason to happen that for the SMR, either not available due to maintenance, inspection, or interruption, or due to licensing. And I will show a couple of examples about the marine, that the nuclear cannot enter certain territory because of their legislation or the policy, cannot have nuclear in their territory. Then we can use the renewable to compensate and balance the region, the balance the energy supply. So what we are doing here is, number one, nuclear renewable hybrid energy system. Number two, nuclear renewable micro hybrid energy system, which is in the level of a microgrid in the small scale. So that's what we have been talking about. Now, in order to raise this point, we have to ask ourselves a number of questions. Number one is a strategy. Like, we understand that the nuclear power plant primarily generating thermal. And based on the thermal, we are actually generating electricity. That is a generator, turbine generator. So eventually we are getting out of the nuclear reactor is a thermal, but also we are getting the thermal can be translated into electricity. So the first thing come to our mind is the coupling. Now, why we need to study the coupling is because the nature of nuclear renewable might vary. Like fuel cell has certain input, which is electric, and then from the electric we get the hydrogen, and from the hydrogen we get electricity. So it's like power, gas power. Now, for flywheel, for instance, as energy storage, we supply a little bit electricity, we store it, and then we generate electricity at a certain later time, which is good for a number of reasons, for high inertia, but also for as energy storage to balance certain peaks, to shift the peaks or to balance the peaks. Also, we have a number of typical technologies like a PV. So I can use the pointer. So here we have here is the PV, and here is the hydropower plant. Here is the wind. Here is some load, which is, we call it electric load or thermal load. And here electric energy storage, like a battery. And based on that, we started, like I would say, developing the profiles. So the load profile, and as we know that you are designing a system to meet a certain requirements. So the certain requirements, it is the load profile. We have to understand clearly what is the load profile, and based on the load profile, we start designing this configuration, and based on the configuration, we start developing the control strategy, and based on the control strategy, we apply the optimization to optimize the control mechanism to achieve the best possible performance. So in this case, we have nuclear power plant, and we have biomass power. And as you see, the dotted line here, this dotted line, as you see here, we have three possible lines. One of them is the hydrogen. This is like large dotted, and here is the small dotted thermal, and the solid, which is electric power. So this is thermal, nuclear power, here is the thermal, and here is the dotted with the hydrogen power line, or the pipeline, or the network, or the grid. So from the nuclear power plant, including the thermal conversion to electricity, that means it generates power to that line. From the biomass, you input thermal, you get, of course, like a burning, and you get electricity. So here the electricity goes to the power line. And then here we have thermal load. So by this way, we have here a possible way to bring the thermal load as a sink, but the source we need E to H, which is electricity to heat, which is E to H, which means we can have any possible different technologies that can act as E to H, and that will get the electricity and will generate the thermal, and that thermal will be coupled here with the biomass and thermal load. The other side, we have fuel cells so that generate electricity. Here it can have flywheel as energy storage. Here is electrolyzer, which get hydrogen and get electricity and generate hydrogen, and from the hydrogen it goes to the fuel cell. Now imagine that I have a small controller here. So if we imagine, yes, oops, I want to change this. Imagine that you have a small controller. So imagine that you have here a small controller, here a small controller, and each one of them a small controller. By this way, we are able to have this I would say distributed controller and supervisory controller for this. I would say we call it SC, supervisor controller, that will control the whole infrastructure based on certain requirements. For example, if based on the price of the hydrogen of the electricity price, the weather forecasting, and the load profile, thermal load profile, and based on those, we are able to sustain locally here, but also extend, because this network can go like here. This hydrogen network can go somewhere else. This electricity can go somewhere else, and this thermal can go somewhere else, which means this is a sort of a unit, and that can be integrated. So that's what we call it here, direct coupling. So we are directly coupling the renewable energy, electricity generated from different resources, and directly link it to the load. We can have also some different styles of coupling, and some of them we call it multi-product based coupling, which means if you see here that now the nuclear power plant, it has clearly defined that now we are generating thermal from the nuclear power plant, and we are getting also electricity from the nuclear power plant. By this way, we are able to take each of them, and that will take us to the possible ways of integrating multi-products. So we are now getting multiple products from the nuclear power plant, whether it's thermal or electricity. And the thermal, we can get thermal waste from nuclear in a number of ways, of course, from the condenser area, from the tower, but also we can get it from the reactor itself in a number of ways. So we have those aspects of getting the multiple products from the nuclear power. And again, who decides what is the best? You have to have, that's coming to the same KPI. So in order to decide what strategy is good and the bad, you need to define, first of all, what do you need? Because simply you can actually have here petrochemical processing. So you can have the electricity or thermal to produce petrochemical or electrical or chemical product. Even the hydrogen itself, the hydrogen as a production, you can produce that by the thermal or by the electricity. As of now, we are producing the hydrogen by the electricity, but there are some other like copper chloride cycles with different cycles that you can actually you can generate the hydrogen by electrochemical process. Now we can have more complicated, that is multiple resources and multiple products. So now, as you see here, we can have the different resources coming with the multiple products coming out from the nuclear power plant. So we can see here that we are able to say, okay, we can have a thermal storage, thermal load in the thermal side with biomass power plant and nuclear reactor thermal, and also E to H, which is electricity to heat. So that's one side. And then we have also the other side, which is H to E, which is you can get the thermal and you can generate electricity here, and that goes to the line here, where it goes to that line, which electric load, and also can go to the electric storage. So imagine that you are able to manage all this picture with in-out based on pricing, price of electricity, price of gas, price of maybe of course the levelized cost of all those resources, but also the weather prediction and the load profile of thermal and load. So we are able to optimize this picture based on our needs and our criteria, I would say. Of course, there are other parameters, could be the regulations. Like now with I would say, like I can say that I need 80%, let's say I need 80% of the hydrogen, yes, of the fuel cell. I need 80% of electricity to be generated here. Now, this is a parameter we can actually dictate. So we can specify how much percentage do we need to generate electricity. For example, from fuel cell, I need 80%. Of course, 80% is too high, but I'm just giving an example. And maybe 5% from maybe E to H, H to E, and maybe 10% from SMR, and so on, and so on. So each parameter here can actually be parameter, each value or each generation capacity can be parameterized and configured based on the optimization criteria and the control structure that will execute the optimization criteria. Now, how to do that? Sorry, it is a very small picture, but I'll just explain it in a simple way. That definitely we would like first to you'd like to see what are the resources and load availability, and you get the profile, and then you will say, do we have adequacy to actually sustain, or do we have a need to start looking into utilizing in any of these. So imagine that we are putting parameters here, like this is A, this is B, and so on. Each of these is actually parameterized and controlled. And parameterized means either on, off, means yes or no. And number two is how much amount with time. So we can actually apply this algorithm with a 1 hour ahead. We call it like prediction with 1 hour ahead or 1 day ahead. And that is a prediction with optimization to tell us actually what is the number one, the size of the PV, the size of the storage, electric storage, the size of the thermal load, and the size of the flywheel, and the size and the capacity of each other unit, like E to H, which is electric to heat, and H to E, and also the fuel cell. In addition, if we are considering that the SMR is one of the parameterized to configure to say what type of SMR you need and what is the size of SMR, then that could be also parameterized. So we can define the number of parameters we would like to consider, and we would like to also consider the control strategy. Means, for example, one of the control strategy here is you would like to store energy in the flywheel as the energy storage. You would like to store energy in the battery first, in the off peak. When the price is very cheap of electricity, you store energy. And when the price is very expensive, you would like to use electricity. So when we have here on peak, off peak. In Canada, we do have this on peak, off peak in most of the provinces. I guess it varies. I guess in US also the same. So that means you would like to optimize the size, but also the control strategy. Are you going to install to store fully in the midnight the energy storage, electric storage, and the hydrogen storage and the thermal storage? Because you can store energy here by simply getting the electricity here in the off peak and store hydrogen. So you are storing hydrogen in the off peak. By this way, you are actually able to save cost and also balance the demand to meet the peak demand in price and amount. And by this way, your hydrogen is ready for the peak, and also the electricity is ready, as well as the thermal is ready. So in the midnight, we don't need thermal, or people are like, we don't need electricity, sorry. And maybe in the midnight, the weather is very cold, so we'd like to increase the heating. In the midday, you'll have the sun, so you'll have more thermal, and so on. So the balance between them, that is what we call it here, energy management algorithm or scheme, including the control strategy. Similarly, when we have this multiple, like single source, but multiple, then multiple products. So we have here the thermal and the electricity and the hydrogen. So now we are able to actually combine the picture, and we complicate here, because now we can say, do we need to store thermal more or store electricity more? I did not talk here about, for example, units like CHP, combined heat and power. So CHP, which is combined heat and power, where we are able to have natural gas coming in, and the output are two. One is thermal and one is electricity. So we're able to generate thermal and electricity as output of the CHP. So by this way, we are able to actually have more high coupling mechanisms between the gas and power. And the algorithm, this is a template algorithm, and we tested with number of scenarios to achieve the best possible optimization criteria for that scenario. Again, as you see here, like, it is not only that we are optimizing the sizing, but also optimizing the control strategy, whether we fully store the electric battery or electric storage, like electric energy storage, or we store in the flywheel, or we store in the thermal, and how much. And as we know, one more thing I would like to say, you see, this is two-way. So for electricity, when electricity goes here, it has $1. When electricity goes out, that is actually $2, which means when you store one kilowatt in the energy storage, it goes with a price. When it goes out, it goes with another price. Who will decide the price? That is energy, transactive energy, or energy accounting or economy, where we can actually define the value, and we can and that is like sometimes in Canada we have OPA or ISO, where they actually estimate the price and they dictate the price among utility companies to regulate the price. So what we are saying here is that the price goes into the energy storage is typically different because of the timeline. So it is different time, that means we are able to get that if $2 is more than, should be more than $1, we are doing well, because now we are actually getting profit and from energy storage, and that's how it's calculated as ROI and the installation, but also how this can compensate the picture of nuclear power plant as a baseline. I will show a couple of pictures. So the same way, this is again other algorithm, multiple sources, multiple products, and a couple of things now for the parameters. Now we started doing in the optimization. Is that nuclear reactor, we have certain parameters. For example, the size, the lifetime, we consider 40, it could be 60, and that's parameterized. We can change the parameter, we can rerun the optimization. And we are considering MMR, a macro modular reactor, and then that's here we have the capacity, we have the total capital cost, sorry, and we have the maybe first unit deployment cost, and then we have the rate of cost reduction, and we have a number of installations. And based on that, and here we are actually using some parameterized values like fixed operation and maintenance cost, $1 per kilowatt electricity, and fuel cost, $1 per megawatt hour, and so on. So we have sort of parameterized, which we got it from some references, and to be realistic. And based on the parameterized, we started looking into different each component. So we took the PV, we said, okay, our target is to get the net present cost, which is net present cost is a sort of like, because you need to standardize and unify the cost at a certain point. So we consider for the PV, what is the number of panels, and what is the instantaneous PV efficiency, and what is the area, and what is the solar irradiance, which is kilowatt per meter square, and so on. Based on those parameters, we actually modeled that for January up to December. And based on that, we are able to get that irradiance data as a sort of model parameters or model like model input to be able to use it for our simulation model. The same for the wind. The same way we parameterize the wind. So we have here the wind based, the power generated is related more or less to, of course, the V mix minimum maximum with the wind speed, as well as the power law exponent, as well as the height of the like the wind, which is 16 meters here we consider, and based on that we estimate the wind. And the same for hydro, we estimate the hydro, and based on that we get the biogas generator and the parameter for flywheel, and those are the different fuel cell, electrolyzer, and the hydrogen tank. We got the model, and we got the thermal, electric, and thermal storage, again the model, and the H2E and E2H, we got the model. And based on that, we define certain parameters. Those are parameters that we are able to change as we want. So for example, you can change if we go to a certain region or the capital cost is different, we can change it, and automatically the system will recalculate and optimize. So we got that for the wind turbine, for the PV, for the flywheel, for the fuel cell, biogas, and so on. Hydro turbine, the turbine, and so on. Electrolyzer, tank, electric storage, thermal storage, and so on. So based on that, we started looking into profile. What do we need to achieve? Like, what is the target? What is the demand? What is the load that we need to meet? So we captured that load profile for electric load profile and thermal load profile. And now our target is to program and model and optimize our configuration for nuclear renewable to meet that profile. So we got a certain profile for electric and thermal from January till December, and we captured them in a certain time frame. So if you see here, it's 24 hours. So from here, from 0 to 20, so it's 24 hours. And based on that model, we said, okay, we need to optimize. What do we need to optimize? So we need to capture everything, we bring it back to the net present cost. So even if you have efficiency, reliability, energy served or energy not served, and so on, all those performance parameters, we bring them back to equivalent net present cost. And the idea here is to reduce the net present cost. So we capture the generation, the temperature, the thermal, the electric, and all those power, thermal, and electric. We capture all of them. And based on that, we try to put some constraints. Because we can either put them as optimization function, as objective function, or we put them as constraints. Some of the decision making, we rather prefer to put them as constraints because of the fact that we don't know exactly like what is the best way, but we can swap them between either constraints or we can put them as objective function. So we actually defined list of objective functions, and based on that, we were able to make the simulation runs. So we have here using different optimization algorithms. So it's different runs and different parameters. We use them to actually do the simulation. So here we have a conversion so that we are trying to get the net present cost to achieve like number of iterations. And that each iteration we reach up to maybe 200, 190 or something, we reach the conversion. And that is where we believe that this is the best possible combination between them. And a couple of things we would like to achieve here is that we keep changing the wind and the solar and the sizes so that we can achieve the smallest possible net present cost of the hybrid system. Now, in order for us also to validate that, we applied some sort of sensitivity analysis. So as you see here, we said, okay, what if we change a little bit the capital cost of the battery? So we say plus minus 5%. What if we change the capital cost of fuel cell? So those to allow us to get a better understanding of what would be the impact of any minor changes of any of these input parameters to the output, which is the net present cost, we apply this sensitivity analysis to apply variations of any of the values of net present cost and how this will be impact the output. And that will allow us to know which parameter is more sensitive, and that is where we use it for also design and validation. So after doing all those analyses, we were able to do some combinations between different parameters, and based on the input we change, we get the output. And we were able to actually apply also sensitivity analysis, where we are able to show that if we change 5 plus minus 5%, we are able to get how much improvement in the net present cost. And that will allow us to use it for also considering some design issues. Like if, for example, the capital cost of the battery is crucial, then we can focus more into the capital cost of battery, or of course SMR or MMR or some other parameters. So that allowed us to see what could be the possible, I would say, impact. Also, the profitable and reliable hybrid energy system. As a conclusion, we compared number of case studies, which is either nuclear alone or renewable alone or nuclear renewable. We have actually 4 cases, and based on the 4 cases, we achieved that. Based on that, the most effective one is the nuclear renewable. Based on this configuration, after optimization, and with sensitivity analysis, we came to the conclusion that for the provided load profile, the nuclear renewable hybrid energy system is the most effective one in terms of net present cost, with considerations of technical aspects of each of these technologies. Now, I would like to spend a couple of points about applications. We do have nuclear power plant outage happen a number of times, including Fukushima. So that motivated us to think about what about we develop a microgrid with SMR or MMR that will be integrated with the nuclear power plant. So at a certain point when they have outage, it is able to cover the needs for the safety system class 1 to 3, and also will be able to sustain the operation for emergency. And that will allow, of course, to have safer shutdown and safer resilient operation during emergencies and during abnormal conditions. So we start looking into that. So that's why I say class 1, 2, 3, 4. And we thought about first implementing that microgrid with fast charging with flywheel into the class 1. And that's where your system should be all the time up and running, cannot be 1 single minute down because of the safety requirements. Class 2 might be 1 hour, class 3 maybe 1 day, class 4 maybe more, and so on. So we were able to design different applications for that. Another point we have been using actually is charging for marine. So we went through the marine. We understand that if you know that the ship can go 1 kilometer, can cost us less greenhouse gas and less gas if it go compared with a car or a truck. So if you would like to make transportation through the marine or through the ships or through the ocean, that would be cheaper and also less greenhouse gas emission, because of the fact that if you move 1 kilometer or 100 kilometers per marine, that will cost us less gas and less greenhouse gas emission. So that's where we went through that exercise to analyze the marine ship. And we developed actually, that's where that we published a couple of work. I will show it in the references. And I didn't put much here because the paper were actually under review, but now the paper is just accepted last week. So, and the other one is now, we received a couple of minor comments to review. So, but the idea here is really to implement the system into marine ships. In addition, I was talking about, sorry, before that, I was talking about that actually, if you go in this ship, it has a nuclear, and if it goes to a certain territory, like for example, Germany, they said we don't need nuclear. So, or certain areas due to some legislations or like policies. So what we are doing is that we put in the nuclear reactor here as a contained in one unit. So when the ship goes to near the seaport of a certain region, this will be disconnected. So we keep the marine or the nuclear reactor away from the territory. Sorry, and then the ship will go actually to the seaport, and that is without the nuclear reactor running with the renewables, and that is a shorter distance. And after that, when it goes, of course, we can also use the pushing and pulling techniques and so on. A couple of things as a final is that monitoring nuclear renewable integration as deployment, we do need data centers and data analytics. So we did some work actually with data analytics, which is before, if you go to any utility company, you will find that they are only monitoring energy in out, power in out. But what we are offering here, we are trying to emphasize on the efficiency, conservation, safety, and reliability. So if you have a pump, when you look to the pump from efficiency point of view, you will look to power, the output efficiency for pushing, and how many hours working as efficiency for differential pressure, but you look to the input power. Now that's efficiency, but conservation, that's another factor we would like to consider for each component, which is how much you are actually saving energy. Safety is a probability of not failing, or safety is freedom from unacceptable risk, and the reliability is a probability of not failing. And accordingly, we are capturing all those factors among the points. And deployment, we have in Canada, if we would like to deploy those in different regions, including remote areas in northern regions, we are able to capture those data and actually implement it with like a sort of infrastructure to implement and monitor those. Yeah, and finally, as I mentioned, this can be implemented in different aspects: energy, water, transportation, food, especially now with different challenges. Health is related to food, related to energy, related to water. So I started looking into this picture as hybrid energy systems. Finally, I'm just looking to the time, just to be on time. Most of my talk you can see in my book published with Elsevier, Smart Energy Grid Engineering. This is a link, and you are most welcome to view this book. And also I published recently another book. It's called Energy Conservation, Residential, Commercial, and Industrial Facilities with Wiley and IEEE Press. And I have a couple of conferences like SMC. I was also chairing a couple of, I was a general chair, but we had some sessions about smart energy as well. And we have also SAGE, which is Smart Energy Grid Engineering Conference. That's every year in August. This year also, so you are most welcome to publish and submit papers in our conference. Of course, this year is virtual still. Hopefully next year will be physical. I'm also CEST. I'm I would say the founder of CEST, which is an annual conference. Last year, 2020, in Turkey. This year, I think in Finland. Previous year was in Portugal. Yes, Portugal. And the previous year was in Spain. So I have some talks in Chicago, transportation, electrification, and some teams from Jiangsu and China as well, and Nanjing. And these are recent publications, but these are especially the two papers I was talking about. So this paper is analysis of nuclear renewable hybrid energy systems for marine ships. So it's published already. That's Energy Reports, just published last week, actually, or like we came to know just a couple of weeks, I think. And the other one, which is optimal planning for integrated nuclear renewable system for marine ships. This is final review. We are just finalizing this. Will be the final review, and will be we received like a minor comments, so we are finalizing. That's all what I have, and thank you very much for your time, and I will be very happy to answer any question.
Thank you very much, Dr. Gaber, and if I may start with a question. You talked about optimizing the microgrid to minimize NPV. Does the approach change significantly if the grid is connected to the network and can buy and sell electricity? And or are you primarily considering microgrids? And do you have an islanded microgrids, I should say? And could you comment in general on whether there's differences between those cases?
Yes, this is a very good question, because definitely it will vary. We have a local optimization within the grid. So always the objective function will vary. Like if I'm within the microgrid, I have a certain objective function to meet the load with minimum cost, and I don't care about the grid or the network or other places. If I'm looking to the other microgrid, I'm also optimizing my microgrid, and I don't care about others. Actually, I had a master's students. We have done which we call it resilient interconnected micro energy grid. So what we have done, actually, we developed the optimization algorithm with game theory. So the game theory looks like, you have two players, and each player try to maximize, and with negotiation and cooperation between them, they come to the point where everyone's satisfied. So we actually, that was the master thesis for interconnected micro energy grids. We applied that for a train microgrids, interconnected microgrids around the railway. And that's also possible. So that will be very useful algorithm, I believe.
That sounds really interesting, and it would be great to read more if you have any document you could share.
Yes, absolutely.
Thank you. Does anybody else have any questions? Okay, well, thank you again, Dr.
Thank you very much.
And it's it's been great hosting you today. And as I say, we'd be very interested to read some more of your publications and stay in touch.
Absolutely. Thank you very much, and have a wonderful day.
Could we get a hold of your email, Dr. Gaber, just to ask any follow-up questions?
Absolutely. I will. I have my email. I believe you have my email. And actually, how can I send it? Maybe you can forward to them if you like.
Yes, I can forward it.
Okay. Okay. Yeah. With pleasure. I look forward to your communications, and feel free to join our conference. And thank you very much for your inviting me. Thank you very much.
Thank you.
Goodbye.